So in this video lecture, we'll see about the Hartley and Colpits oscillator. So this is Dr. Mohalakshmi, Professor and Head Department of ECE from Rohini College of Engineering and Technology. So Hartley oscillator is a type of harmonic oscillator which was invented by Ralph Hartley in 1915. These are the tuned circuit oscillators which are used to produce the waves in the range of radio frequency, and hence they are also referred to as RF oscillators. Its frequency of oscillation is decided by its tank circuit, which has a capacitor connected in parallel with the two serially connected inductors as shown in the figure. You can see that there is a red box enclosure where you have two inductors and one capacitor, where this particular part is called as a tank circuit. So here RC is the collector resistor, while the emitter resistor RE forms a stabilizing network. Further, the resistors R1 and R2 form the voltage divider bias network for the transistor in CE configuration, that is common emitter configuration. And next, the capacitors Ci and C0 are the input and output decoupling capacitors, while the emitter capacitor Ce is a bypass capacitor used to bypass the amplified AC signals. All these components are identical to those present in the case of a common emitter amplifier, which is biased using a voltage divider network. However, figure 1 also shows one more set of components, that is inductors L1 and L2 and the capacitor C, which form the tank circuit. On switching on the power supply, the transistor starts to conduct, leading to an increase in the collector current IC, which charges the capacitor C. On acquiring the maximum charge feasible, C starts to discharge via the inductors L1 and L2. This charging and discharging cycles result in the damped oscillations in the tank circuit. The oscillation current in the tank circuit produces an AC voltage across the inductors L1 and L2, which are out of phase by 180 degree as their point of contact is grounded. Further, from the figure, it is evident that the output of the amplifier is applied across the inductor L1, while the feedback voltage across L2 is applied to the base of the transistor. So you can conclude that the output of the amplifier is in phase with the tank circuit voltage and supplies back the energy lost, while the energy fed back to the amplifier circuit will be out of phase by 180 degree. So the feedback voltage, which is already 180 degree out of phase with the transistor, is provided by an additional 180 degree phase shift due to the transistor action. Hence, the signal which appear at the transistor's output will be amplified and will have a phase shift of 360 degree. So this satisfies the criteria. So at this state, if one makes the gain of the circuit to be slightly greater than the feedback ratio, which can be given by beta is equal to L1 by L2 if the coils are wound on different cores, and it also can be given with L1 plus M to the ratio of L2 plus M, where M indicates a mutual inductance. So if it is going to be in the same core, then the circuit generates oscillations which can be sustained by maintaining the gain of the circuit, which is equal to the feedback ratio. So this causes the circuit in figure 1 to act as an oscillator, as it would then satisfy both the conditions of the Bernoulli criterion. So the frequency of such an oscillator is given by 1 by 2 pi root of L effective C. So L effective is the summation of L1 and L2 if it is combined in the, or if it is wound on the different cores. Whereas it will be equal to L1 plus L2 plus 2M if the coils are wound on the same core, where M indicates a mutual inductance. So next, coming to the Colpits oscillator, it is again a type of LC oscillator which falls under the category of harmonic oscillator invented by Edwin Colpits in 1918. So the coming figure shows a typical Colpits oscillator with a tank circuit in which an inductor L is connected in parallel to the serial combination of capacitors C1 and C2, which is shown in the coming figure by the red enclosure. So here you can see C1 and C2 it is connected in parallel with the L inductor, which is a tank circuit. So this gives you the Colpits oscillator. So other components in the circuit, as usual, it is found in the case of common emitter configuration, which will be having a voltage divider network, RC, RE, or the collector resistor and the emitter resistor, which is used to stabilize the circuit, and R1 and R2 will form the voltage divider bias network. Further, we have the, as usual in the previous case, we have the capacitors Ci and C0, which are the input and output decoupling capacitors, while the emitter capacitor is the bypass capacitor, which is used to bypass the amplified AC signal. Here, when the supply is on, the transistor will start to conduct, which will increase the collector current, due to which the capacitors C1 and C2 get charged. On acquiring the maximum charge possible, they start to discharge via the inductor L. During this process, the electrostatic energy stored in the capacitor gets converted into magnetic flux, which in turn is stored within the conductor in the form of electromagnetic energy. Next, the inductor starts to discharge, which charges the capacitor once again. Likewise, the cycle continues, which gives rise to the oscillation in the tank circuit. So first, the C1 and C2 will keep charging, and once it reaches a maximum charge, it will be discharged through the inductor. Once the inductor keeps discharging, again the C1 and C2 will charge. So this gives you a sustained oscillations through the tank circuit. So here the figure also shows that the output of the amplifier appears across C1, and thus it is in phase with the tank circuit's voltage and makes up for the energy which is lost by resupplying it. On the other hand, the voltage feedback to the transistor is the one obtained across the capacitor C2, which means the feedback signal is out of phase with the voltage at the transistor by 180 degree. So this is due to the fact that the voltages developed across the capacitors C1 and C2 are in opposite polarity, as the point where they join is grounded. Further, the signal is provided with an additional phase shift of 180 degree by the transistor, which results in a net phase shift of 360 degree around the loop, satisfying the phase shift criterion of Barcushian principle. So here also there will be a 360 degree phase shift. So here you can write, or the frequency of oscillation can be given by the feedback ratio C1 and C2, which is carefully has to be monitored. So the frequency of this type of oscillator depends on the components in its tank circuit, which is given by preferably L, which is the inductor, C effective, which is the effective capacitance of the capacitor, expressed as C1 C2 divided by C1 plus C2. So as a result, these oscillators can be tuned either by varying their inductance or the capacitance. However, if the variation is in L, it will not have a smooth variation. Hence, usually the capacitances are varied, which are generally ganked, due to which a change in any one of them changes both of them. Nevertheless, the process is tedious and requires special large valued capacitor. Thus, the Colpits oscillator are never preferred in the application where the frequency varies, but are more popular as fixed frequency oscillators due to their simple design. They offer better stability in compared with the Hartley oscillator, as they are exempted from the mutual inductance effect present in between the two inductors of the Hartley oscillator. Thank you.